Hey everyone, welcome back to Everything is Relative with me, Mr. K. And today we're going to be doing something a little different since there aren't any topical past paper questions on the Papa Cambridge website on the topic of medical physics for Cambridge A-level physics. I've put together some questions from recent exams, from past year exams in the recent years on the topic of medical physics. And I'll share a link to these questions in the description of this video. And you can download them, and I will share the mark scheme as well. You can download them, go through them, and use this video as a guide, and we can do some work together to try and understand how to solve questions on medical physics. Now, yes, this topic is mostly theoretical. It is mostly just theory, a lot of reading and understanding, but there are quite a few calculations as well, and they sometimes can get a little tricky. And so it's good to just complete what is incomplete. And I've put together a selection of 7 questions. In this video, I'll do the first 4, and in the next video, I'll do the final 3 questions. Since they're quite long, and some of them count quite a few marks, so it's something that you have to be prepared for. So the first question I've put together comes from, again, the subject code is 9702. It comes from the winter 2023 exam, winter being October, November. Comes from question paper 4, variant 1, and it's question number 10 from that paper. We're told that ultrasound and X-rays are both types of wave that are used in medical diagnosis to form images of internal body structures. We're told a complete table 10.1 for each type of wave. Complete table 10.1 to state for each type of wave the method of production of the wave and whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted by the internal body structure. Okay, so basically we want to know how ultrasound and X-rays are produced. Very simple. You can see there's not much space in this table. And then we want to know if the detected wave for ultrasound and X-rays are the absorbed, reflected, or the transmitted waves, the things that we actually do the detection on. So firstly, how do we produce ultrasound? So I have very little space, so I have to make sure that what I write is very brief, and so I don't need a very long, complicated explanation. But how is ultrasound produced? Well, it's produced by the rapid vibration of quartz crystals. And that's what a piezoelectric crystal is. When I cause the crystal to vibrate rapidly, I generate ultrasound waves. So it's caused by the rapid vibration of quartz crystal. What about X-rays? How are X-rays produced? Now we should know that X-rays are produced when electrons strike a metal target. So I can simply say X-rays, the method of production is electrons hitting a metal target. And that's good enough for how these two types of waves are produced. So they're very different in nature, and their method of production is also very different. Next, we want to know whether the detected wave for ultrasound and X-rays is absorbed, reflected, or transmitted. Now, ultrasound, we know that the sound wave goes into the body, is reflected at the point between boundaries, and then we detect the reflection. So the detected wave for ultrasound is the wave that has been reflected of the boundary between structures with different acoustic coefficients or acoustic impedances. And for X-rays, we know that X-rays go into the soft tissue, they then get absorbed by bone, and that which hasn't been absorbed by bone passes through the rest of the soft tissue out the other side of the body and is then detected. So be very careful. What we actually observe, what we actually detect is not what's being absorbed. Obviously, if it was being absorbed, we wouldn't be able to detect it. So what we actually detect for X-rays are the waves that are transmitted. So the waves that actually pass all the way through. So we send it in one end, detect it at the other end, and that's the transmitted wave. And so those are a quick 4 marks, but again, we have to understand ultrasound and X-rays for this one question. We're then told that for one type of wave passing through tissue, the wave has 72% of its initial intensity after it has passed through 6.2 centimeters of the tissue. And we want to find the linear attenuation coefficient mu of the tissue for this wave. So it could be either, it could be ultrasound or X-rays, but if I'm looking at the intensity, then the intensity that passes through this amount of tissue I is equal to the intensity that goes in, the initial intensity I naught, times e to the minus mu x, where x is the distance through the tissue that the wave has traveled. So this equation applies to X-rays and ultrasound. And so what I know is that the final intensity, the measured intensity, is 72% of the initial intensity. So 0.72 I naught is equal to I naught e to the minus mu x. And what I want to find is the linear attenuation coefficient mu. And so I can see I naught disappears from both sides. I can then also I can lineify both sides. That is, I can take natural logs of both sides of this equation, and I get minus mu x is equal to the natural log of 0.72. So the attenuation coefficient mu is the log of 0.72 divided by minus x, which is minus 6.2. We leave it in centimeters because they want the value for mu in per centimeter. And so what I get is 0.053 per centimeter. That's already in two significant figures. 0.053 per centimeter is the linear attenuation coefficient for this type of tissue and for this type of wave as well. We actually don't know what type of wave it is, either an ultrasound or an X-ray. And so that's the linear attenuation coefficient mu for the tissue. We're then told that another wave of the same type as in B1 passes through 9.3 centimeters of the same tissue, and we want to calculate the percentage of the initial intensity of the wave that is attenuated by the tissue, that is absorbed. We're only assuming that the attenuation or the amount of energy lost by the wave is happening due to absorption. So we want to know how much of the wave is absorbed after it passes through 9.3 centimeters. So the percentage or the amount that is transmitted, we know from the equation above. That ratio of what comes out over what goes in is the percentage that is transmitted, I over I naught. And this is e to the minus mu x. Well, this is e to the minus 0.053 times 9.3. We're leaving it in centimeters. Since mu is per centimeter and the distance is in centimeters, so that works out fine. And what we get is a value of 0.611. This is 61%. And so the amount that's absorbed, if 61% passes through, is everything else. And so the attenuated percentage, the percentage of the wave that is attenuated, is everything that's remaining. It's 100 minus 61, which is 39%. And so 39% of the wave is attenuated. That means 39% of the wave is absorbed by tissue, and only 61% passes through. So you can see it doesn't take a very long distance through tissue for there to be a significant amount of absorption. And that's what we have to consider when using these technologies for medical diagnosis. So that is a question that you could have used ultrasound or X-rays, but the mathematics was the same. And in total, that question was worth 8 marks. And it was quite interesting. We had to understand both X-rays and ultrasounds in order to answer this question completely. The next question is number 2, as I've numbered it. It's from the winter 2023 exam. It's question paper 4, variant 2, and it's question number 9 from this paper. And again, it's going to be questions that are later on in these papers because the medical physics and cosmology usually come towards the end of the exam. We are told that fluorine-18 is a radioactive nuclide that is used as a tracer in positron emission tomography in PET scanning, and fluorine-18 decays to a nuclide of oxygen according to this equation. Now the first thing we want to do, and we can also see that this is, if we remember carefully, how this occurs, PET scanning occurs when there's a beta decay. So that knowledge that this is going to be a beta decay will help me with this question later on. But first I want to state what is meant by a tracer. And it's important again that you know what a tracer is. So remember, a tracer is any substance that, when introduced into the body, will be absorbed by the tissue that you want to study. So I can say it is a substance or material introduced into the body that is absorbed by the tissue being studied or being observed. So if I want to study a particular tissue, I must introduce a tracer that's going to go towards that particular tissue when it enters the body. And if it does so, then we're using the correct tracer for the job. So it's some substance that we introduce into the body that will be absorbed by the tissue in question. We're next told to state the symbol of the particle that is represented by X and the values of P, Q, and R. So the nuclear equation on top is not complete. We have to make labels for X, P, Q, and R. Now, the first thing I'm going to do is, well, I know that this is beta decay. And if you remember, you know that it's beta plus decay. But it's either going to be beta plus or beta minus decay. And that's what PET scanning uses. So you have to know that. So the first thing I'm going to do is actually find the value for P. Because if I balance atomic numbers, if I balance proton numbers, then I should have that on the right-hand side, P plus 8 must equal to the atomic number on the left-hand side, which is 9. Which means that P is equal to 1. And so immediately I see that the nuclide X, whatever that may be, has an atomic number of 1. But we know this is beta decay, so that must be a beta particle. It does not have a nuclear number. It's a positron. Positrons don't have nuclear numbers because they are not nucleons. And so immediately the value for Q is 0. And by that assumption, obviously, I now know that it has Q value of 0 and a P value of positive 1. So the nuclide X is a beta plus particle. It is a positron. You can say E plus or beta plus. It's basically the same thing. It's a positron. And the remaining thing is R. Well, what would the value for R be? Well, 0 plus R must equal to 18. And so R is simply 18. So it is oxygen 18 that is produced. The nuclide of oxygen is oxygen 18. And so this was, I could start from one end and then figure out value by value. I didn't have to go clockwise or anti-clockwise or any of that. And so that requires knowledge of PET scanning if you want to answer this question successfully. Next, part B, Roman numeral 1 says, explain how the radioactive decay of fluorine-18 results in the emission from the body of the gamma ray photons that are detected during a PET scan. So even though beta decay happens, we don't detect the beta particles. What we detect are gamma rays. So they want to know where the gamma rays come from. Explain how gamma rays come into the equation if we are talking about beta particles. Now, what we remember from quantum physics is that positrons and electrons, the particle-antiparticle pair, they will do something special. We use a very special word to describe them. They will annihilate each other. And they will annihilate each other inside the body. That's because positrons, once released by the decay, don't have to travel very far until they find an electron. So they annihilate each other inside the body. There's an abundance of electrons inside the body. And the mass of the particles cease to exist anymore. So believe it or not, mass is lost in the universe. The mass of the particles is converted into the energy of the emitted gamma ray photons. And there will be more than one photon. As you should know, there are two photons being released when a positron and electron annihilate each other. But that kind of question might come by later on. So positrons and electrons annihilate each other inside the body, and the mass of the particles that initially existed disappears, and Einstein said E is equal to mc squared, so it's fine because the equivalent amount of energy is released in the form of gamma ray photons. And those are the gamma ray photons that we detect. Next, we want to explain how the detection of the gamma ray photons is used to produce an image of the tissue being examined. Okay, so there are multiple ways to state this, but what we basically do is we look at the arrival times of photons using our ring of detectors around the patient, and the arrival times of photons are processed. Again, we need a fairly good computer to do the analysis, and we take all of these arrival times, put the data together, and we create an image. And so an image can be created of the tracer concentration in the tissue that we are studying. And so the tracer is radioactive, it goes into the tissue that we're studying, it undergoes beta decay. The beta particles don't travel a far distance, so they're very close to the tissue in question. When they collide with the electron and give off gamma ray photons, the gamma ray photons exit the body, they're picked up by the detector, and the detector tells us, they're coming from that point in the body, and so we can tell that there's high activity happening in that body that usually could be a sign of a tumor or other abnormalities. And so we use the arrival times of photons to create an image and then understand the tracer concentration in the tissue. Part C says the half-life of fluorine is T, and the patient is injected with the amount of substance N of fluorine 18. We want to determine an expression for the initial value R0 of the rate R of production of gamma ray photons by the tracer in terms of N, T, and the Avogadro constant. Wow, okay. So this is a question that we would not have seen anywhere in our theory when we were studying the topic, but we need to suddenly derive an expression for the initial rate at which gamma rays are produced. Now, what we are actually looking for is the activity. So R is related to the activity because the activity is the number of decays happening per unit time. But remember that for every occurrence of annihilation, there are 2 gamma rays produced. So this value R is actually 2 times the activity because there are 2 gamma rays produced for every collision. And what we remember about the activity from nuclear physics, the activity is the decay constant lambda times the number of radioactive nuclei n. Well, this means that in the initial rate R0 of gamma ray production is equal to 2 lambda n0, where n0 is the initial number of particles that we have. But wait a minute, I don't have lambda. They asked me to find the expression in terms of n, t, and na. So how am I going to do this? Well, I know lambda, t is the half-life, but I know that the half-life is log 2 over lambda. So similarly, lambda is log 2, the natural log of 2 over the half-life t. And I don't know the number of particles, but I do know that the amount of substance in moles is little n. So what I know is number of molecules is number of moles times Avogadro's number, 6.02 times 10 to the 23 molecules per mole. And so the initial rate then becomes 2 times the natural log of 2 times the initial amount of substance n times Avogadro's number Na divided by the half-life t. So we had to use knowledge of radioactive decay from nuclear physics and understanding that when gamma rays are produced, they are produced 2 at a time. So we had to multiply this rate of the reaction, which is the activity, by 2, and everything else was deriving from the expressions that we already knew from radioactive decay. So again, you may have never seen this equation before, but it's important that you know how to work with the mathematics to be able to derive an expression like this. We're not completely done with the question just yet. The final part of the question says on figure 9.1, sketch the variation with time of R. Well, it's radioactive decay. And so initially I have R0, and then the number or the activity drops exponentially. R naught e to the minus lambda t. And what I know is that after one half-life, half the initial value remains. So after a single half-life t has passed, the value of R naught is a half R naught. After two half-lives have passed, 2t, I have a half of the previous value, which is a half R naught. A half of a half is a quarter, or a quarter of the original value. So what I have is I have an exponential decay, and it's going from R naught to a quarter R naught in a time of two half-lives. So I need to make sure that this graph is not a straight line, and I also need to make sure that it passes through the points that I've plotted. So again, it's going to be a lot easier if we do this in pencil, but it's going to have a negative gradient throughout, and it's always going to be a curve. And so again, mine is not going to look amazing here simply because I'm not using a pencil. But there we go. Assume that this is very curvy rather than straight, and the gradient's always negative, and it's an exponential decay over the first two half-lives. And so that's what the rate of the reaction tells us, that the half-life means that the rate is dropping by half its value, two half-lives means it's dropping to a quarter of its initial value, and so on. And so that was a fairly long question that altogether was worth 12 marks and required us to go back and understand the things that we learned in nuclear physics. Question 3 comes from the summer 23 exam. That's May-June 2023. It's question paper 4, variant 1, and question number 8 from the paper. We're told that table 8.1 shows some data relating to the properties of air, gel, and body tissue, and the data are given to 3 significant figures. We have a table here that seems to be incomplete, but before we get ahead of ourselves, the first question says, show that the specific acoustic impedance of gel is 1.68 times 10 to the 6 kg per meter square per second. So I'm given values of the density, the speed of the sound, and the specific acoustic impedance. And I can see that all of the values are given in correct SI units, so I'm actually thankful for that. It means at least I don't have to convert. But I want to find the specific acoustic impedance, which is Z, for gel. So the last row in the last cell in the second row here is missing. What I know is Z is the density of the medium times the speed of sound in that medium. Z is rho times C. This is just by definition. It's a definition of specific acoustic impedance. And the value for rho is 1,200. The speed of sound in the substance in gel is 1,400. If I multiply them together, guess what I get? I get 1.68 times 10 to the power 6 in the correct units. That's kg meter squared per second. And so I can actually put this value in, 1.68 times 10 to the power 6, which is actually identical to the cell below it. The relevance of that will become clear later on. As you may have thought, the next question is to complete the table by calculating the missing values to 3 significant figures, and we given space to work to do our workings. So the first thing I want to do is maybe calculate the speed of sound in tissue, and then I'll find the density of air. So the speed of sound in tissue, I'll just call it C tissue, is equal to the acoustic impedance of tissue, Z, divided by the density of tissue, rho. And for tissue, the value of Z is 1.68 times 10 to the power 6 divided by the density, which is 1090 kg per cubic meter, which gives us 1540 meters per second. So I can actually put that value in, 1540 meters per second. Next, I want to find the density of air. The density of air is acoustic impedance of air divided by the speed of sound in air, which, if I use the values from the table, is 440 divided by 340, and I get a value of 1.29 kg per cubic meter. And so I can complete the table now by saying the density of air is 1.29. And so this is what your table would look like. So you need to understand the relationship between the acoustic impedance and the speed of sound in that medium. So this is a very ultrasound-like question. We're then told to use the information in A to calculate the intensity reflection coefficient for an air tissue boundary. Now the intensity reflection coefficient, we sometimes call it alpha. We remember, and this will be in your formula sheet, this is Z1 minus Z2 all squared divided by Z1 plus Z2 all squared. Now, as you can see, the order of subtraction and addition is not really important. We're squaring the value anyway, so you could subtract either way, the numerator will remain the same. So you don't have to concern yourself about the order of subtracting. And all of these values I know, the values for Z1 and Z2 will be that for air and that for tissue, which I can simply get from the table, the specific acoustic impedance for those substances. And so this is 440 for air minus 1.68 times 10 to the power 6 squared over 440 plus 1.68 times 10 to the power 6 squared, which is 0.999. It's nearly 1. 0.999, three significant figures. So that's a very large intensity reflection coefficient, which means that almost all, 99.9% of the wave is going to be reflected. Hence, you can see the hint here, this is why we use gel. Because if we had air between the ultrasound device and skin, most of the ultrasound will just bounce back off the skin and not go into the body. 99.9% of it will be reflected, and only 0.1% will actually go in. What about a gel tissue boundary? So again, alpha is Z1 minus Z2 all squared over Z1 plus Z2 all squared, where Z1 and Z2 here are the values for the specific acoustic impedance for gel and tissue. Again, we get that from our table. And this is 1.68 times 10 to the power 6 minus 1.68 times 10 to the power 6 all squared over 1.68 times 10 to the power 6 plus 1.68 times 10 to the power 6 all squared. Now you can clearly see what this gives us. This gives us 0. Obviously, in reality, it's close to 0, not exactly 0, but it's approximately 0. The intensity reflection coefficient is 0. So between the gel and the skin, or the gel and the tissue, there's very little reflection. So all of the ultrasound wave actually goes in. And that's why we use the gel for ultrasound, to not allow a lot of the wave to be reflected off the skin when the ultrasound device is placed on it. And the next question asks specifically that. Use your answers in B to explain why gel is applied to the skin during ultrasound scanning. So we have to write it in a nice way. So we'll say that without gel, nearly all of the incident, now it's important to use the correct terminology, the incident ultrasound is reflected by skin. Not going to be much help if it's not actually going into the body. But if I change that and I add gel, almost all of the ultrasound or ultrasound waves is transmitted into the body. So I can actually use it to image inside the body if it actually goes inside the body. And so this is why we use gel. So without gel, most of the incident ultrasound is reflected by the skin, goes back out. But if we use gel, almost all of the ultrasound passes into the skin, into the body, and then can be used for imaging inside the body. So this question was very strongly focused on the topic of ultrasound. But again, we need to be able to be prepared for anything that comes our way for medical physics. And so that was in total, that was an 8-mark question. The next question comes from the summer 23 exam. That's May-June rather, 2023. It's question paper 4.2, and it's question number 10 from that paper. We are told that X-rays for use in medical diagnosis are produced in an X-ray tube. In the X-ray tube, charged particles are accelerated towards a metal target by an applied potential difference. And we want to state the name of the charged particles that are accelerated by the applied PD. As we should know, just from the top of our head, that the particles that are passed through a potential difference in the production of X-rays are electrons. So electrons are accelerated to a very high speed, and then we strike them against a metal target. So those are electrons. We then need to explain how X-rays are produced at the metal target. So we only want to know how X-rays are produced. They didn't ask us anything about how they are used for imaging. We just want to know how the X-rays are produced, and specifically when they strike the metal target. So what happens is that electrons are decelerated, and specifically decelerated by the collisions that they undergo with the metal atoms, with the atoms of the metal target that they strike. So what happens when the electrons are decelerated? They lose energy. The energy lost by the electrons becomes the energy of the X-ray photons that are produced. So the energy lost by the electrons is then emitted as X-rays. So by decelerating the electrons, by electrons losing energy when they collide with the metal atoms, they give that energy. That energy is given off in the form of X-rays. So E is equal to HF for the energy of the X-ray photons. And that's how X-rays are produced at the metal target. We then want to find the minimum wavelength, the cutoff wavelength of X-rays produced when the applied potential difference is 5.8 kilovolts. So whenever you see a question like this, the best thing to do is to first go to your conservation of energy. I give the electrons energy EV because the electrons have charge E and their potential difference that I accelerate them through is V. So I give them initial potential energy EV. All of that potential energy is eventually converted into energy of the photons. Energy of photons is hc over lambda, which means that I can find the wavelength, at least the minimum wavelength, which will give me the maximum energy, lambda, if I assume that all of the energy EV is being given to a photon, an X-ray photon, so that's a minimum wavelength and maximum energy. Lambda is hc over EV. H is Planck's constant, 6.63 times 10 to the minus 34, multiplied by the speed of the electromagnetic wave c, 3 times 10 to the 8 meters per second, divided by E, which is the charge of the electron, 1.6 times 10 to the minus 19, and the potential difference is 5,800 volts, or 5.80 times 10 to the power 3 volts. And what I get is this wavelength will be 2.14 times 10 to the minus 10 meters. All of my values are in 3 significant figures, so my final answer can be in 3 significant figures. 2.14 times 10 to the minus 10 meters. So that's the wavelength, or the minimum wavelength. The maximum energy corresponds to this minimum wavelength that can be given to the X-ray photons, assuming that all the initial potential energy is converted to energy of the photons being released. We are then told that X-rays pass through a medium that has an attenuation coefficient of 1.4 per centimeter, and we want to calculate the percentage of the X-ray energy that is absorbed, again absorbed, by a 2.8 centimeter thickness of this medium. So we've already done a question that's very similar to this, where we said that the transmitted intensity, the amount that goes through, is I over I naught. And this is equal to E to the minus mu x. So whenever you hear absorption or attenuation, you immediately go to this equation. And this is equal to E to the minus 1.4 per centimeter, multiplied by moving through a distance of 2.8 centimeters. And this is 0.0198. So that's approximately 2%. So 2% of the initial intensity of the X-ray travels through a distance 2.8 centimeters. So if only 2% moves through, is transmitted, what happens to the rest? The rest is absorbed. So how much exactly is absorbed? Well, everything besides the 2%. So the amount that's absorbed, the absorbed percentage, we can call it, since that's what the question is asked for, the absorbed percentage is 100 minus 2, 98%. So 98% of the incident X-ray is being absorbed, and only 2% is allowed to be transmitted through, which is essentially what we want for X-rays. Unlike with ultrasound waves, where we want a reflection, with X-rays, we want much of the X-rays to be absorbed, and the little that goes through can then expose the film on the other side. So the percentage absorbed is 98%. And the total for this question is 9 marks. And again, this question was actually purely focused on X-rays. So you can see the questions can be mixed. You could do an entire question based on only one diagnostic tool. X-rays, ultrasounds, PET, whatever. And you have to understand it well, and you have to understand things like the attenuation coefficients, transmission absorption, the acoustic impedances, the reflection coefficients. All of these things are important. Because yes, this is a very conceptual topic, but there's mathematics embedded in it as well. And more than likely is going to be the case, you will find a question that will include some sort of problem solving. And a 9-mark question in a 100-mark exam is 9%. So you wouldn't want to leave this question blank or let it go because you aren't really sure how big of a percentage it's going to cost overall. And so I would suggest taking the time to read, understand, and get a grasp of how to do the mathematics, because it's really not that difficult. And so in the next video, I'll complete this paper, and I'll leave a link to this paper down below. So make sure to download this, solve it first before you watch this video, and then use the video as a guide to see if you're on track and if you're doing the correct things and so on. I'll also leave a mark scheme so that you can just refer to where the marks are being allocated for each question. But also wording is very important, since there's a lot of writing in this topic and explaining and describing and so on. I hope this video was useful. I hope this topical past paper questions are useful, and I will do another one of these for astronomy and cosmology at some point. But if this really was helpful, please leave a like and a comment, subscribe to the channel if you haven't already. And from me, Mr. K, that's all for now. I'll see you again next time when everything is relative.